Hello everybody, it's time for video 5 of lecture module 5, the video I did not plan on having, but it just seemed like a good logical break to go ahead and stop talking about all the orbital stuff with Mercury as we transition to global views of Mercury and start discussing Mercury's surface as a planet. I've done something a little bit different with this video than I do normally with class. And I have tried to include lots of images that I just normally don't have time in class from the NASA Messenger mission of the surface of Mercury, so you can get an appreciation of what the surfaces of these planets look like, because these are entirely different worlds. And with every planet that we talk about, one of the things I always mentally try to do is imagine what it would be like to be on the surface of that planet. It would be an entirely different world. And these are every planet out there, and the larger asteroids and the Kuiper Belt objects are worlds unto themselves. So let's take a global view of the planet Mercury. And from 2011 to 2015, the NASA Messenger mission visited this planet. It was not the first spacecraft to visit it, but it did revolutionize our knowledge and our view of Mercury. Prior to Messenger, we did not have a complete map of the surface. We now have a complete map of the surface with high resolution, and you can see both sides of the planet right here. So Mercury is an airless body, is dominated by surface craters. It's had a surface sitting around for about the past 4 billion years without any alteration, closer to 4.2, 4.3 billion years, just accruing more impact craters. As an airless body, it has no erosion, so impact craters become the dominant surface feature. The color on this is a little bit exaggerated to show you differences in ages of the surface and some information about difference in composition on the surface. That's not quite what it looked like to the naked eye, but pretty close to it. So let's go ahead, and before we continue, one of the important global things about Mercury is that Mercury is a land of extreme temperatures. And it is a very, very hot planet as well, given that it's the closest planet to the sun, a semi-major axis distance of 0.39 AU, the closest planet to the sun. It is a very, very hot planet. It does not, however, have the highest surface temperature. That honor it belongs to Venus. And I'll explain why Venus has a higher surface temperature, yet still it's further away from the sun when we start talking about Venus in the next lecture module. One thing that Mercury does have, though, is the largest daily temperature variations. And remember that a day on Mercury, a solar day, is 2 Mercury years. So it has 1 Mercury year in daylight and 1 Mercury year of nighttime. So over those time periods, and being that close to the sun, you get an extreme range in temperatures. The daytime maximum temperature is about 700 Kelvin. That's 430 degrees Celsius, or nearly 800 degrees Fahrenheit. That is a toasty, toasty planet. The nighttime minimum, it can get extremely cold at night with no atmosphere to regulate its temperature. It just cools down, and it can get as cold as 100 Kelvin. That's minus 173 degrees Celsius, or minus 280 degrees Fahrenheit. Over 1,000 degrees Fahrenheit temperature variation between the day-night cycle on Mercury. It has the largest daily temperature variations of any of the planets in our solar system. The polar regions are pretty interesting as well. So typically the polar regions in daytime, they can get pretty hot. It has hot poles about 400 Kelvin. However, there are some very, very extremely cold regions, less than 100 Kelvin, that persist at the poles of Mercury, because Mercury has permanently shadowed craters. It has almost no axial tilt, just like the moon. So it has at the poles permanently shadowed craters. And there is a plethora of evidence that, just like with the moon, in these polar permanently shadowed craters, there is water ice. So despite being the closest planet to the sun, it's very, very likely that Mercury does have water ice on it, just in these permanently shadowed craters at the poles. Now I want to go ahead and show you what that would look like and switch to some of these global views. So here's a temperature map of a Mercury polar region. So what we're looking at here is a map of the North Pole. The red color is about 400 Kelvin. And then these purple colors, these would be our permanently shadowed craters right here. Purple is about 50 Kelvin, cold enough to sustain water ice for the age of the solar system. And also you can see now what Mercury's surface looks like. Uh, let's go ahead and look at a non-temperature map. So here we're looking at the South Pole, so we switch to the other pole. Not overly different. What are you actually seeing here? You see rough, smooth, well, you see lots of impact craters, and between the impact craters, you see sort of these smooth plains. A compositional analysis revealed that that is volcanic material, so you have these volcanic smooth plains. Sounds kind of like the smooth volcanic plains of the lunar Maria, and their formation is not that different. Just taking another view. So again, you can see all of those smooth plains, but otherwise surface dominated by craters, and between the craters, the smooth plains. But here in this large view, we can see that Mercury has enormous cliff faces. And it's even cutting through this crater right here. So this cliff face right here is going to be several kilometers tall. So a rock climber's dream. And it's over 400 kilometers long. So Mercury is covered with these long cliff faces, and geologically, these cliffs are called scarps. Just zooming in, since impact craters are one of the dominant things that we see on Mercury, what do they look like? And here we can see the Monchot or Monchot, not quite sure how to pronounce it, crater. This crater is 106 kilometers in diameter and even has craters within it. You can see that the sun is coming from the top. You can see that this has been flooded by lava because it has these smooth volcanic plains with only with a smaller number of impact craters overall, and just a bunch of small impact craters in there. And here you can actually see another one of these scarps going through this crater. Okay, so now that we've had a nice global view and looked at what the surface of Mercury looks like, let's try to characterize it. Let's come up with the surface of the Mercury and try to come up with the major terrains like we did on the moon. The major terrains for the moon were the lunar cratered highlands, and then we had the lunar Maria. So as we were seeing on Mercury, and for this, we'll use this other global image over here. You have all of these old, ancient, big impact craters, and between the craters, you have these smooth plains, gently rolling hills, think like Kansas or Oklahoma, sort of topography between there. We know that they're volcanic rock, they're basalts. But we have these smooth plains in between the craters, covering about 45% of the entire surface of Mercury, these types of smooth plains. Since these plains are what exist between the craters, let's bring to bear all the creativity that we astronomers use at naming things, and let's call these smooth plains between the craters the intercrater plains, the plains between the craters. Nailed it. So good at naming things. Well, astronomers are really good at naming things. This is the oldest part of the visible surface. So we're looking at the oldest surface, and it dates by crater count to about 4 billion years old. So the surface of Mercury is about 4 billion years old at its oldest. Something kind of cool, all of the larger craters get names. It's just a thing that we do in planetary science where we name our craters. Every planet has its own naming conventions and traditions, and the one on Mercury is one of my favorite traditions, where all the impact craters are named after artists. So writers, musicians, painters, pretty much any kind of artist you can imagine out there. So some of my favorite crater on Mercury happens to be the Tolkien crater. I'm a big fan of Chekhov as well. Not going to discuss William Faulkner, brilliant writer, just not my cup of tea. There's Van Gogh. So I encourage you, I've provided a link to the list of craters on Mercury. Think about who your favorite artist or series of artists are and see if there is a crater on Mercury named after them. Sort of an interactive, fun sort of thing to do. But if we're going to talk about surface features on Mercury, we have the Intercrater Plains, and then we have the impact craters. relatively boring to talk about, except we can spice things up a little bit. And here I'm using spicy as in let's make it more interesting and hot as well. And let's talk about this very, very, very large impact basin that appears on the surface of Mercury. It's the easiest way to tell if you're looking at a picture of Mercury or if you're looking at a picture of the far side of the moon is look for this impact basin called the Caloris Basin. Caloris in Latin means hot, same root as where we get the word calorie from. And this is an absolutely enormous impact basin. So again, what is an impact basin? It is a very, very large impact crater. Here we have a planet. Here we have a very large impactor. Hits it, creates a very, very large impact basin, a very, very, very large impact crater. So large that we just call it a basin. And Caloris Basin is the largest single surface feature on Mercury, and it is one of the largest impact basins in the entire solar system. From edge to edge, it is just shy of 1,600 kilometers. That's 1,000 miles. Within the crater, since this is clearly going to be a complex, not a simple crater, it has those concentric rings in it, and these concentric rings are mountains up to 2 to 3 kilometers high, over mile-high mountains. Whatever whacked into Mercury right here. So here comes the impactor. This is a little bit too large to actually create something like that, but we'll go with it since these are the tools I have in hand. Whenever it hit, creating the Caloris impact basin, you can imagine that's going to be quite the energetic event. It's going to create some serious seismic activity in the planet Mercury. And that those earthquakes, those seismic waves are going to go around and through the planet and converge on the direct opposite side of the planet. That's going to be some crazy earthquakes, magnitude levels that I don't even want to hazard a guess at how powerful they would be. And it's going to create havoc on the surface of the planet on the direct opposite side, what would be called the antipode point. And this is what's going to be called the weird terrain. It looks like a jumbled up terrain, almost as if the surface got smashed up and turned into a jigsaw puzzle. Well, I do want to take a closer look before I talk a little bit about the weird terrain. I want to give you a better view. So here is a falsely colored for emphasis view, looking straight down onto the Caloris Basin. And this is a combination of two images. It took one image when sunlight was falling directly down onto this, so it wouldn't really have any shadows at all. And then any brightness variations are variations in how reflective the surface they are. So that detects albedo variations. So how do you get different albedo? You have slightly different compositions of what the material is. And then there's another one taking at where the sun is at a higher incidence angle so you can recover the shadows. So it looks sort of natural. So the way that they colorize this is the orange colors are lava, where lava flooded and coated this basin. And then the blue colors are low albedo material, so low reflectance material. And I just want to give you a view of what this impact basin, this Caloris Basin looks like. But remember, this impact is going to be super energetic. It's going to hit, send seismic waves streaming all the way through Mercury, wrapping around it, going through it. They're all going to converge on the direct opposite side, creating some serious, that's me simulating the earthquake that would have resulted, the Mercury quake, and it would have jumbled up the surface on the direct opposite side, and in fact it did. So on the direct opposite side of the planet from the Caloris Basin, we have what we call the weird terrain, because it doesn't make any sense. It's a very strange looking terrain. That's a very jumbled up surface. So we call it the weird terrain. Again, really great at naming. You can see it here is a fairly large swath. This is 800 kilometers across. All right, so that's all I have for lecture module 5. I cut out the last bit of material. We'll just tack it on to the next lecture module. Hope you enjoyed starting to learn a little about Mercury. I encourage you to look up the Messenger mission. Maybe use that as one of your extra credit, online extra credit assignments. Look up the Mercury mission, describe it, detail it, and clearly you have something to talk about how that mission relates to class now. Thank you for tuning in, and I will see you in next week's lecture modules.